Hello everyone, my name is Kyung-shin Lee. I'm working at LG Electronics. I'm going to present ECS, a new snapshot-based debuting solution on NAND flash memory. The demand for fast boot has been increasing in many consumer electronics. For example, rear-view camera system for automobile. It should be ready immediately after driver started the engine for their safety as well as conveniences. A lot of effort have been made to reduce the boot time. It can be reduced by optimizing cold boot, but it costs a lot of efforts and time in general. Also, it is not easy to apply for other devices. Persistent memory claims less than 1 second booting. Unfortunately, the maturity of the technology is still in progress, and the price has not reached a realistic level. Snapshot booting is generally quicker than the cold boot. However, the method yields extra weight to the NAND flash memory, so it will bring reliability issues due to the limited lifetime of NAND flash memory. Our proposal is to extend a lifetime of NAND flash in snapshot booting. Most snapshot booting techniques focus on traditional magnetic disks. A study improved snapshot booting by reducing snapshot image size. However, it used Linux kernel swap space that works for traditional magnetic disks. Other approaches based on NAND flash require detailed analysis to reduce booting time. For example, a study keeps a status or type information of the latest flash memory to reduce the file system mount time. Our work differs from these studies. We used snapshot booting on NAND flash, focusing on reducing write traffic and WAF value of flash memory. And our approach is more general to apply to the devices. ECS is a new snapshot booting solution for modern NAND flash memory. We have designed it to optimize the lifetime of NAND flash and implemented it on Linux kernel. ECS is placed between power management and block I/O layer of Linux kernel to manage write traffic and write amplification factor, as you can see in Figure 1. Figure 2 shows a traditional snapshot booting process. We have merely made changes on 3 parts of the suspend and region process. Our main contributions can be summarized as follows. First, we propose ECS focusing on improving the lifetime of NAND flash. Second, we introduce various techniques such as file phases isolation, deduplication, compression, logo structure, physical segment management, and garbage collection to reduce the snapshot image and WAF value. Lastly, we quantitatively analyze the improvement of lifetime and boot time with the ECS over a traditional snapshot booting on real-world device. Snapshot image is a status of memory on suspend. Generally, a bigger snapshot image leads to more time to boot a system because it takes more time to read the snapshot image. We found out Memory workloads affect snapshot image sizes through our experiment. In this paper, we categorized memory workload in the following 4 cases to see how each memory workload affects the snapshot image size. The snapshot image is made up of pages with various usages. So we break down a snapshot image into pages. Next corner means a page as basic unit of the memory system. To study the characteristic of the pages, we first observe the usage of each page in the system and categorize them into 3 groups. This chart shows the result of our experiments on how each workload affects page sizes of a snapshot image. It shows the size of a file, same and unique pages of a snapshot image across different memory workloads. According to our experiments, snapshot images that can be reduced are slightly different on each workload. File page size increases the most on random workload due to running many random applications. Snapshot images can be reduced by on average 18% further by deduplication on same pages. We can perform the comparison at the end to reduce the image size further. Originally, a snapshot image is no longer used for the next suspend phase. It means that the image is created every suspend phase without knowing previous snapshot image. After some investigations on such snapshot images, we found that some pages across multiple snapshot images are duplicated. If we utilize these duplicated pages, physical write traffic can be reduced. This approach should be effective when there are more duplicated pages across multiple snapshot images. Figure 4 illustrates this idea. Figure 6 illustrates first 500 sample pages in real snapshot image at the first 3 suspend phases. In the previous slide, it is explained that duplication across multiple suspend phases could reduce write traffic. But we found there are some limitations on using that method. Snapshot images cannot be stored at some point due to space limitation. The unused space should be overwritten to overcome this limitation, but it decreases the duplication ratio. Degree of fragmentation gradually increases and slow down the booting time due to overwriting. Figure 5 shows the read I/O counts at each region phase. As you can see, it gradually increases over time. This will result in degradation of booting time. We will discuss how to resolve this later. These are our 3 key design considerations. We designed ECS based on these considerations along with the snapshot analysis results. To reduce write traffic, we have applied these 4 techniques. This chart shows the process of reducing a snapshot image step by step during the suspend. First, file page isolation is performed to isolate file pages from the snapshot image by releasing them. Second, to eliminate duplicate pages of the image, kernel same page merging is conducted. Third, to reduce write I/O requests, inline duplication is performed. Finally, the remaining pages are compressed. As a result, the final write traffic decreased by nearly 91.8% than the original size. To reduce WAF value, we designed these features. First, one of the key design considerations is to make the unused data structures with a careful consideration of NAND flash characteristics. As illustrated in Figure 7, ECS divide the whole volume into fixed size segments. A segment is a basic unit of measurement in ECS and consists of consecutive blocks. These units are aligned with the operational units of the underlying FTL layer. By aligning the units with the FTL, ECS can make a small and constant WAF value. Second, we present a log structure segment management. For each write I/O request, the segment manager locates segments in an offend-only manner and keeps track of all segment allocation with the segment information table so that it can continue controlling WAF over time. The last key design consideration is to perform garbage collection so that the FTL layer can manage invalid blocks in advance and resolve its storage efficiently. Garbage collection is a process to reclaim those invalid blocks scattered throughout the memory. We found out that duplication across multiple suspended phases causes snapshot image fragmentation. To solve this issue, we designed a segment-based duplication feature. The key idea of the method is to minimize the performance degradation of reading the snapshot image at the expense of the reduced duplication ratio. HSD makes the whole data segment into two groups, hot segment and cold segment. ECS performs the duplication only from hot segments. The segment manager locates data segments with an offend-only manner. New data segments for new unique phases are located without further fragmentation. This makes new data segment be allocated from the data section as consecutively as possible, which effectively mitigates read performance degradation. We have evaluated ECS on an Android in-vehicle infotainment system. We allocated a 1.5 GB partition of EMMs, which is used to store snapshot images. And we ran suspend and resume on each workload for 10 times. We also compared ECS with a traditional snapshot putting technique. Figure 9 shows the write traffic of LKS and ECS. On average, the write traffic on ECS decreases by 2.8 times. In terms of WAF, however, it is difficult to estimate the value without the knowledge of FTL, which is normally not accessible by end users. So we extract all the I/O pattern from ECS and ask the EMM manufacturer to simulate the pattern to get WAF value. The simulated WAF result of ECS is 1.1, which is almost same as the theoretical best value of 1.0. However, it is still difficult to simulate the I/O patterns from LKS because the I/O patterns are completely random every time. For fair comparison, we assume the best and worst case from another study. Table 1 summarizes the estimated lifetime in a year. We implemented both LKS and ECS on bootloader. The bootloader can read the snapshot image directly after system initialization, eliminating the time required to start the Linux kernel. We measured 10 consecutive boot times from power on to resume complete and calculated the average. Figure 10 gives an average booting time over 10 runs. We can see that ECS is always faster than LKS across all the workloads. ECS is 1.5 times faster than LKS on average. Figure 11 and 12 show that write traffic and boot time result of multiple phases. The result clearly shows that it remains nearly constant over multiple phases. In Figure 11, write traffic at the first phase is higher than other phases. This is because of the fact that an inline duplication cannot happen at the very first suspend. This chart shows the correlation between hot segment threshold and write traffic. Figure 13 shows how write traffic and boot time changes on idle workload as hot segment threshold is varied. We see that as hot segment threshold increases, write traffic also increases because the more cold data segments are likely to be reclaimed. On the other hand, boot time decreases as fragmentation is improved. Once the threshold gets close to 100%, write traffic increases dramatically. We see similar trends on other workload, and we found that our hot segment threshold of 90% provided a good boot time with reasonable write traffic. The results in this paper have been shown with a threshold of 90%. Although booting time is greatly reduced with ECS, as booting is repeated, it increases gradually. This is due to the fact that the duplication technique inevitably causes data fragmentation, resulting in degradation of read I/O performance. To solve this issue, ECS introduced HSS method. We present an experiment that captures the intuitions of the design of HSAD rather than extensive evaluation results that span various workloads. Figure 14 clearly shows that DOF with HSAD remains nearly constant over time, while DOF without HSAD grows quickly. Figure 15 also shows that the boot time with HSAD remains unchanged over time, so we can effectively handle the degradation issue of the boot time if DOF is well controlled with the HSAD method. However, we observed that the duplication ratio dropped between 12 and 31% across our workloads when the HSAD method is applied. We also observed that the suspend process was delayed by up to 3.9 seconds. A conventional snapshot booting on NAND flash can bring a real reliability issue. To handle this issue, we propose ECS solution. Experimental results show that ECS can significantly reduce write traffic and make the WAP value of 1.1, resulting in 2.45 to 126 times longer lifetime. Moreover, ECS can reduce the booting time by 1.5 times than our traditional snapshot booting. We conclude that ECS is a promising solution that can enable the snapshot booting on many consumer electronics. Thank you very much, and if you have any questions, please feel free to contact me.